In this lecture, I will basically discuss the how to test for linear restriction with the help of GMM estimator. Next, I will derive how to derive covariance estimator by allowing the case of heteroscedasticity and or autocorrelation. Next, I will discuss how to derive feasible GMM estimator, that is, if we allow the problem of heteroscedasticity as well as autocorrelation. In the last class, we have introduced the concept of generalized method of moment estimator. Now, in this class, let me start my discussion with test for over-identifying restriction for the linear model. Now, we have already seen that we can have more number of instruments than that is required. That is, we have a case of over-identification. Now, for the time being, let us consider that we are considering a linear model, and suppose there are L number of instruments that is available and K number of parameters to be solved. So, that implies the degrees of freedom left is L minus K, where L is the number of instruments and K is the number of regression. Such a model implicitly incorporates L minus K number of restriction. Now, problem arises because generalized IV estimator implicitly uses only K effective instrument. Now, let W star be the n cross L minus K extra instrument. This implies L dimensional span of full set of instrument is generated by linear combination of the extra instrument W star. Now, the over-identifying restriction requires that the extra instrument should not be correlated with the error term. Although we do not observe U, what we can observe is the estimated vector of U by IV residual, call it U hat. Thus, we can check whether this U hat vector is correlated with the extra instrument W star. Now, consider the model that we wish to test y equal to xb plus u. Now, testing the over-identification restriction implicit in the model is equivalent to testing it against the alternative model y equal to x beta plus w star c equal to w star c plus u. Now, the alternative model is constructed in such a way that it is just identified. There are precisely L coefficient to estimate, namely the K elements of beta and L minus K elements of C, and there are precisely L instrument. Now, one possible way to test is to obtain instrumental variable estimator and obtain U hat. Then perform the regression U hat is W star times B plus residual. Now, if B equal to 0, W star and U hat is not correlated. That is, in the first step, we are using instrumental variable estimator. From that, we obtain the values of U hat. Then we are performing then we are regressing U hat as a function of W star, that is, we are regressing U hat on W star, obtain the values of beta and then test whether beta is equal to 0 or not. If beta is equal to 0, we say that U hat is not correlated with W star. Now, the test statistics for this is basically the explained sum of square from the regression divided by the estimate of the error variance. Now, error sum of square is basically the criteria function that has been minimized in order to arrive at the instrumental variable estimator. Now, the use of such statistics is proposed by Hansen 1982 in the famous paper that first proposes GMM estimator under that name. So, it is often called Hansen's over-identification statistics or Hansen J statistics, but it is preferable to call this as Hansen-Sargent statistics to stress its close relationship with the Sargent test of over-identifying restriction in the context of generalized IV. Now, let us then discuss the covariance estimator. Now, choosing the right weighing matrix is most important for GMM estimator, because the expression for GMM estimator in turn depends on the choice of the right weighing matrix. There have been many econometric papers written on this subject. Now, estimation results can be sensitive to the choice of the weighing matrix. Now, while deriving the weighing matrix or covariance estimator, till now we have not considered the possibility that heteroscedasticity and autocorrelation be a part of our model. Now, how to take account for this? Now, if we want to take into account the problem of heteroscedasticity as well as autocorrelation, we need to modify the covariance matrix in the presence of heteroscedasticity and autocorrelation. Now, let us first consider the case of heteroscedasticity. Now, in the presence of heteroscedasticity, one can perform White correction. Now, under White correction, the diagonal term of the estimated variance covariance matrix will represent the heteroscedastic variance, and off diagonal form or off diagonal term will be equal to 0. Now, let us note that the W matrix, that is the weighing matrix, can be written as limit t tends to infinity 1 by t. This is a double sum. One is q running from 1 to t and another is p running from 1 to t. mp xt plus I z t beta prime mq xt plus I z beta. So, this is basically the representation of some cross product term representing the MP and MQ, where MQ is the qth row of the T cross N matrix of the sample moments. So, basically you are using the variance covariance matrix, that is the variance covariance matrix among the different explanatory variables. Now, for the appropriate problem, and the weighing matrix are minimization of u prime z, w inverse z prime u, and from the minimizing this expression, you can able to generate the value of the weighing matrix, that is w. Now, weighing matrix can be consistently estimated by using any consistent estimator of the model parameter and substituting the expected value of the squared residual by the actual residual. Note that the only difference here is that we are generalizing the problem by allowing instrument, that is jets. So, since you have more instrument than that is required, you need to construct minimization of this quadratic term in order to arrive at the value of or the expression for the weighing matrix W. Now, the problem next, introduce the problem of autocorrelation. The problem is that with autocorrelation, it is not possible to replace the expected value of the squared residual by the actual value from the first estimation. It would lead to inconsistent estimate of the autocovariance matrix J. The problem is that asymptotically the number of estimated autocovariances grow at the same time and same rate as the sample size. Thus, whilst unbiased W is not consistent in the mean square sense. Now, thus we require a class of estimator that circumvents this problem, a class of estimator that prevent autocovariances from growing with the sample size, or W is equal to J equal to minus T minus 1 to plus T plus 1 omega J gamma J. So if you take such kind of W, you can rule out the possibility that autocovariance function may not grow over time. Now key to choose is the sequence of W such that the sequence of weight approaches unity rapidly enough to obtain the asymptotic unbiasedness, but slowly enough to ensure that variance of the convergence goes to 0. The lag window is expressed as Wj equal to Kj by B divided by Bt. And using this concept, you can get the heteroscedastic and autocorrelated consistent matrix, that is Hack matrix representation, which is equal to W hat, which is gamma hat 0 plus j running from 1 to p kj by pt multiplied by gamma j plus gamma minus j. So, estimating W hat, we are able to provide the Hack matrix estimation. Now, Kj by Bt is a kernel function and Bt is the called bandwidth. The intuition behind is that Bt stresses or contracts the distribution. It acts as a scaling parameter and Kray's rate is referred to as lagged window generator. Now, when the value of the kernel is 0 for z greater than 1, Bt is called the lag truncation parameter. Autocovariances corresponding to lag greater than Bt are given by their weight. The scalar Bt is often referred to as the bandwidth parameter. So, Bt is basically the lag truncation parameter, and autocovariances corresponding to lags greater than Bt are given 0 weight. So, if you have lags greater than Bt, from Bt onwards, the values of the lags are equal to 0. That is, you are not putting, you are basically putting 0 to the weight beyond Bt. Now, in the literature, you have two type of estimator. One is quadratic and other is Bartlett. Now, for example, Niue and West suggest a Bartlett type of function where W hat is equal to gamma hat 0 plus j running from 1 to p 1 minus j by p plus 1 multiplied by gamma hat j plus gamma hat minus j. The expression of W hat guarantees positive definiteness, which is something that we desire since we would look like a positive variance. So, under Niue and West condition, you can ensure the positive definiteness of this weighing matrix W. Now, sometimes we need to pre-whitening of the data, and this has been proposed by Andrews and Mohanan, and you fit a var model of the moment residual where sigma hat is equal to A of sigma hat t minus 1 plus E mu hat, where W hat is the pre-whitening data for W, and this can be written as D hat multiplied by W hat mu multiplied by D hat prime, and D hat equal to 1 minus IA whole inverse. This is known as whitened estimate, and this can be used to any kernel. Now, let us consider some example of the linear model. Now, estimate by IV, which is consistent but it is inefficient, and using this you can get the instrumental variable estimate beta hat equal to x transpose z, z transpose z inverse, z transpose x whole inverse, z transpose x, z transpose z inverse, z transpose y. Now, use this estimate to construct the expression for W now using the expression for W, you can get beta hat equal to z time x prime z multiplied by W hat inverse z time x whole inverse x times z W hat inverse z times y. Now here the iterative procedure can be employed in order to estimate the values of W hat. In practice, after obtaining the Hack estimate, that is heteroscedastic as well as autocorrelated corrected estimates of the variance covariance matrix, we are in a position to generate feasible efficient GMM estimator. In practice, efficient GMM estimator in the presence of heteroscedasticity and autocorrelation of the unknown form work as follows. Here we basically use the iterative procedure. Now in the first round, what we do? We first obtain the inconsistent but inefficient estimate, probably by using the generalized IV. So in the first step, use the generalized IV, and from them you obtain the value of W, and value of W is may be consistent but it may be inefficient. Now in the next step, using the residual from the instrumental variable you had, we obtain the estimated variance covariance matrix either by Hansen-White estimator or Newey-West estimator or by some Hack estimator. Now once we obtain the values of the Hack estimator, in the second round we obtain the new estimate of GMM. And what we get is a continuously upgraded GMM. Now where to stop? Whether we stop after one round or continue until the procedure converges, the estimates have the same asymptotic distribution if the model is correctly specified. So when we find that the estimates have the same asymptotic distribution, then we conclude that the model is correctly specified and stop the upgradation process. That is basically what we do. You take any initial value of instrumental variable, obtain the residual by using that instrumental variable estimator, then using that residual obtain variance covariance matrix, and then using the estimated variance covariance matrix obtain the values of the estimator, the continuously updated GMM estimator. However, there is evidence that performing more iteration, you have improvement in the finite sample observation. As usual, the covariance metric estimator can be used to construct pseudo t-test and other world test, and asymptotic confidence interval and confidence region may also be based on it. So using these covariance metrics, one can carry out the pseudo t-test and other world test, and also can consider the asymptotic distribution of the variables. In this lecture, I have discussed how to test for over-identifying restriction if you assume the linear model. We have then discussed how to derive the covariance estimator if we allow for heteroscedasticity and or autocorrelation. Now, if you have the problem of heteroscedasticity and or autocorrelation, you need to construct the Hack matrix, that is the heteroscedasticity and autocorrelation corrected estimator. After deriving Hack estimator, we are in a position to derive the feasible estimator for the model. we have discussed how to get feasible GMM estimator if you have the case of heteroscedasticity and or autocorrelation. Basically here we use an iterative procedure, that is we start from some initial estimate of the variables and then using that initial estimate you use the estimated value of the residual, and using the estimated value of the residual you go on estimating the variance covariance matrix and hence next round of estimate of GMM. So you are getting an continuously updated kind of GMM estimator, and you stop where the asymptotic distribution of the two estimated remains same after each of the iteration.